Hey everyone. So in this video, we're going to be talking about a very special type of power series called a Taylor series. And this is a series that we can use to approximate any function we want to. Now, again, it has the same, um, conditions of the power series. It's definitely going to converge at a point that it's centered at. But aside from that, it may or may not converge at any other points. And if we're really lucky, it'll converge everywhere. It turns out the Taylor series for many functions that we look at in the calculus class or that you talked about in pre-cal are functions that do converge everywhere, and they're very nice. So anyway, this is a Taylor series. So in this particular series, realize we just have a power series. Here's the power portion of our power series. Remember, it's again centered at some value, in this case x equals c. Our sequence an within our series is given by this front portion right here, and this was supposed to be a C inside there, so I just had to cross that out. And you guys know the policy of the class. If there's a chance that I could make this thing look like it was done professionally, I will not take it. So there you go. Anyway, so this is that sequence right there. And what this n in the parentheses means is it means take the nth derivative of the function. So if you see f parentheses 4, that doesn't mean f to the fourth. It means the fourth derivative of f. And then obviously if we have a function, or sorry, a value like c in here, it means evaluate it at that point c. So basically if we just take out all the terms starting with n equals 0 in this term, that's the n equals 0 term, n equals 1 term, n equals 2, n equals 3, and so on and so forth. Now we're getting these just by plugging those values of n into this particular series, okay? And a gathering of all of these terms, you notice that they follow kind of a polynomial pattern. Like we have something to the first order here, the second, the third. This would be x minus c to the 0th order. So sometimes we'll talk about things called Taylor polynomials, and that just means to what extent of polynomials do we want to take this series out to. So for example, a second order would go just out to this term right here. A third order would go all the way out to this term. But we'll talk about that a little bit more at the end of the slide. So anyway, these are Taylor series. So what I want you to try to do is, as an example, write out the Taylor series for this function centered at x equals 3. And what I want you to do is when you write out the terms, I want you to see if you can recognize a pattern and write this actually as a completely different series. Now you're gonna use this formula in this series to end up coming with some new series that we can represent this function by. So just give that a try real quick. If it's really challenging for you, don't worry. We'll kind of explain a few tactics later in the video. But pause the video and just try to write out that Taylor series. Okay, so if you wrote out the Taylor series, notice one thing you have to do is you'll have to evaluate a function, its first derivative, its second derivative, its third derivative, and so on and so forth. So notice that in the Taylor series, we have x minus c raised to the n. Okay, that's something that's changing with n. We have n factorial. Okay, we've seen factorials in a lot of series before. It's this f to the n prime of c, which is kind of difficult because that's going to change for every single function depending on what its derivative is. So oftentimes when I do problems like this, I like to just write out several terms of just the derivatives and see if I can recognize a pattern in there, because if I can recognize a pattern with the variable n in there, I can just plug that directly back into the Taylor series, and it becomes a lot easier to figure out a different way of saying the same series. So anyway, if we look at the function 1 over 1 minus x, here are our first 4 derivatives, okay? Now, if you didn't get this, again, pause the video, try to take the derivative of this function again. If you're still getting stuck on it, at this point, I'd like to kind of, we got to stop the video for a bad analogy once in a while, and here's going to be one. When you're doing infinite series, and especially the pace this class goes, you got to distinguish between what are problems that are just like flat tire on the road problems. You get a flat tire, you either patch it, get it fixed, or you get a spare in there. But obviously, if you're going to put a spare in there in math, you can't go above 55 miles an hour. Or else you might have the other case where your car is totally broken down, you need to get it towed and taken to the shop. In the former case, if you're not remembering how to calculate derivatives like this, you just gotta, it's like a flat tire for your brain. You got a flat brain, okay? A brain flat. It's easy to fix a brain flat. Just get a patch, go on about it. But if you're having a lot of trouble, actually following the formula of the Taylor series, that's more like, your brain needs to be towed and taken into a shop, which probably is going to require a tutorial session. So anyway, yeah, if you get somewhat confused by these things, sometimes you just gotta, if you're having trouble calculating this derivative, just keep watching the video for now and maybe come back to calculating the derivative a bit later. But anyway, if you do it, you'll notice that a pattern develops, okay? So here, in this case, with that parentheses n, that would be n is equal to 1. Then we'd have n is equal to 2 down here, n is equal to 3, n is 4. So when we look at this, one thing I see is that there's not only a relationship between the power of the derivative and the power in the bottom, there's also a relationship between this top number and that number n. Were you able to figure it out? Well, in this case, if we say n is equal to 1, then 1 factorial is equal to 1. 2 factorial is equal to 2. 3 factorial is 6. 4 factorial is 24. Now, if you haven't worked with factorials, that's kind of a dirty trick, and I apologize for that. But if you have worked with factorials, sometimes you start to recognize certain numbers, and 1, 2, 6, 24 are factorials of 1, 2, 3, and 4, respectively. So we've seen a pattern that develops right here. So this nth derivative we can just write actually as this sequence right here, which is really cool. So now if you didn't get to that point, I'd be very surprised if some people did. But anyway, this is kind of what we can do with Taylor series, so just bear with me. If you didn't get to this point on your own, don't worry. Just start from this point now and plug that value of fn of x back into this for the original series that we had, and see if you can come up with a new way to write this series. So pause the video. Okay, so if we did this, the next thing we can do is we know we want to evaluate this derivative because we're centered at c equals 3. So if we plug 3 into that, we end up getting this sequence right here. Then if we plug that in for our Taylor series, we see, well, these n factorials, they'll cancel out. So we'll just end up with this equation, which really is a form of a geometric series, which we can rewrite like this. In this case, our value a is -1/2, and as long as the quantity 3 minus x over 2 is less than 1, remember that's r less than 1 in the geometric series, then we know we have something that's convergent. Now, we could have also, to get an interval of convergence, just done the ratio test and done that as well. And as we saw in the last video, it comes with the same conditions as a geometric series, so you get the same inequality. But anyway, what I want to get to is look at this right now. We've formulated this series that doesn't really look anything like the original series. Let me clear the ink from this page because it's getting a little too crowded. But yeah, when we look at our original series, it looked like that. But when we were able to find the pattern in the derivative, we were able to rewrite that series as something like this, which looks a little bit different than before. Again, if you're having issues going between these steps, that's like something, ask a question about that during class, just pop in during tutorial. We'll get you sorted out there. But for right now, we just want to understand kind of what we just accomplished right here. We just found a way to write a series approximation for the function 1 over 1 minus x within the vicinity of x equals 3. Okay, so basically if we're around x equals 3, we hope that this series that we just found will be a good approximation for our function 1 over 1 minus x. And you see, if we go through the interval of convergence process, we end up getting this interval. So here's a quick question. What is the radius of convergence of this interval? Well, the radius of convergence, remember, a radius goes away from the center. This thing was centered at x equals 3. That means if we want to go from 3 to 5, we got to go 2. Or if we want to go, or L, we could go L. We could go 2, all right? Or if we want to go from 3 to 1, we could also move 2, but in this case, move -2. So our radius of convergence in this case is 2, and again, our series is centered on x equals 3. So let's look at what this did for us here. Let's go into Desmos. Here, again, the red line is our function 1 over 1 minus x. The blue line is our series. And again, I have, capital N terms that I'm going to keep moving up and up and up, and we'll see um, what happens with this series. And then I also have my bounds that we found between 1 and 5. And I also showed another purple vertical line for our value of x equals 3 where we are centered. Now notice that if we look at just the 0th term alone, when capital N is 0 in our series, again, we still get something that converges to the function at the point we're centered at. Remember that property of power series. But, the blue line doesn't converge anywhere else. I mean, it doesn't look like it matches the red line anywhere except for that point. So again, if we bring up more terms into our series, we see that eventually it does in fact converge on the red line, and it does it within very or pretty tight bounds of that interval we found with a radius of convergence of 2 from the point 3. So anyway, so that's that's what we're doing right here, and yeah, I know some people might be thinking, okay, like what is the purpose of this? Why is this useful? Well, first of all, I'd say, imagine you're in this situation. Okay, you're at a desk. You're doing work by candlelight. Okay, and someone just comes into your room, and you immediately think, why am I doing work by candlelight? It's the year 2016. Well, maybe the reason is because all of a sudden, a few weeks ago, electricity just decided to disappear. So, so we're going back to that again, like medieval times. All right, this civilization, it's gone pretty chaotic for a while, but we're trying to pick up the pieces and restart. You're part of a camp or some kind of colony. You got one person that's a doctor, they save lives. One person, that grows all the food, and then you got you, and now you got to find work. And this person comes up to you and they say, "Hey, I got a job for you. The camp really needs this. This is really important to our survival. We need you to, with your pen and with your paper and with your candle, you need to calculate the square root of e. Can you do that for us?" Because when electricity disappeared, the calculators don't work anymore. So we've all been curious what it is, but we can't just plug it into our calculator. So can you be the person, to do this job for us? It's time you started pulling your weight around here, and you're going to be able to say yes. And on that day, you will be thankful for Taylor series and Maclaurin series. All right. So sorry for that long tirade. And yeah, we're not going to edit this. This is just gonna go in the video. Anyway, actually, Taylor series are really, really useful. They're especially useful when you're trying to solve equations that don't have exact solutions and you need to approximate them. They're incredibly useful to use with computers. And Taylor series themselves have a lot of really neat properties that when you use them in different other types of contexts, some cool things happen. So, but the bottom line is, these are what your calculators use when they calculate certain numbers. And back before the day of calculators, these were very useful. Like I said, if you were in a place with no electricity, if you had to calculate the square root of e, well, you could do it using a Taylor series, because what you're doing is you're breaking down a function, in this case e to the x, to just a series of terms that are nothing more than addition, subtraction, multiplication, division, or raising something to a power. Well, that's PEMDAS, and that's very easy math to compute. It's not easy just to say, all right, what is sine of 1.3? That's something that doesn't really come very naturally. But if you use a series, you can break it up into those simple math terms. So if you didn't have a calculator, you could calculate sine of 1.3 if you wanted to. So those are some of the uses, and we will talk about one more other series in another video that I promise will be very, very brief, much more brief than this one.